stop sharing my screen.
Okay. Okay, so yeah, we'll dive right into it here. But again, yeah, this is just the title slide, and thanks again for inviting me to speak at this. And before I get started with anything, I would just like to say that you can't do this work alone, and I've had a lot of people help me with this and various other projects along the way. But and this is just to name the people: Scott McCallum, Jalal Jalali, Ashley Dowds, and Meryl Stapila, who also all contributed in major ways to various aspects of this work. And I really couldn't have done all this without them. So many thanks to them. There's two parts to this talk. This is based largely on a talk that we gave at ERTEC last year, but I wanted to add some additional insights since then to that. So what I wanted to talk about in the major portion of this talk is our modifications we've made to the gas in place model to account for the gas in place in the EURs that we're seeing coming out of the Marcellus. But there's always talk about what are there other sources of hydrocarbon that these well bores are drawing on from outside of the Marcellus Shale itself. And so I wanted to take some time to address that as well and my current thinking on that. So just a very, very basic review of what we're talking about when we're talking about building a volumetric model is that you start off with a rock sample, and we can break that down into the matrix component of that and the pore volume component of that rock. And then using these different petrophysical techniques, well log data and all that, we can break that matrix volume down into its components, quartz, carbonate, clay, etc. And we can use that to define a grain density. And then the bulk density captures that entire rock volume, including the pore volume and the fluids that are in there. And the difference between those is those porosities, and then those different log signatures are how we're breaking that down into oil, gas, and water in that system there. So this is the approach that we're talking about, is the core to log derivations of all these different components and the issues that we've seen moving forward with that. So the reason I named this talk, giving 110%, is that what we've found is we've started assigning EURs and then occasionally even observing the cume production of Marcellus wells, is that the recovery factors of these rocks are exceedingly high. But what's more concerning is that in some instances, these recovery factors are actually exceed 100%. And so that's obviously called into a lot of question, about, spacing, drainage areas. Are the gas in place models correct? Are they wrong? And this is just an example from southwestern PA, where the gas in place way we've historically calculated is about 94 BCF per square mile. And if you look at the average EURs that have been reported in there, it's about 2 BCF per 1,000 feet of lateral. So if we take a 5,000 foot lateral at various spacings, you get an idea of what kind of recovery factors that we're talking about here. And generally this area here seems to be where a lot of operators that have landed in terms of wellbore spacing. So, again, we're dealing with like 75 to 80% recovery factors, but we do occasionally see wells that are more in the 100 to 110, sometimes even higher percentage range, and we needed to address that. So there's a number of issues that we could look at to explain that. One is that the gas in place estimates that we're coming up with this volumetric model are wrong. They're underestimating the gas in place, and there's actually more in there. And if we had that correct, our recovery factors would fall more in line with something that we're comfortable with. I would also argue it's entirely possible that the EURs are incorrect. This industry, the shale well industry, is it's getting older now, but it's not all that old. And, we're projecting EURs on wells out, to 30, 40, 50 years. And with the modern completion techniques we've been using, some of those wells are only maybe 10 years old or so. And even some of the oldest Barnett wells are maybe only 20, 25 years. So maybe the EURs aren't accurately representing what's going on, although that doesn't explain the cume production. And then, horizontal and vertical drainage, do we really understand that and how that's working? Are our models of these, cylinders of drainage too simplistic? Those sorts of things. So these are all the types of things I want to address. And there is a caveat to this. And one of that is that these issues seem to be a Marcellus Appalachian-based issue. When we talk to people working other plays, and maybe this is incorrect or maybe this is changing, but it doesn't seem like other operators in other basins are seeing these same issues where they have these really high recovery factors. Or maybe you are starting to see that, and this talk would be of all the more interest to you. So that kind of leads us down two different paths. Is that one, if the answers that we come up with to explain this are not unique to the Marcellus, then that would suggest that the recovery factors are extremely low in other plays. The other side of that then is that if this is indeed just a Marcellus issue, then the answers that we come up with are likely the result of characteristics that are unique to the Marcellus and not found elsewhere. And that's why we're not seeing these issues crop up in other basins. So, but to answer any of those drainage volumes, EUR issues, all those sorts of things, we need to have a confidence in our gas in place models. And that was one of the big problems, is that whether right or not, we were losing confidence in those gas in place models and whether or not they were accurately representing what was going on. So we took some effort into trying to modify this. And one thing that what I wanted to do in this talk is focus on the three main aspects of the model that we've focused on. And the one is the Ambrose-Hartman correction, which I think everybody's pretty familiar with, and I'm not going to spend a whole lot of time on that, but it is important to incorporate it into the model. But then I wanted to spend a lot of time talking about measured water saturations in the core, and then this application of a dynamic pore pressure to the model as opposed to a static value that we generally use. So again, in this paper here, this SPE paper, this Ambrose-Hartman correction is very well documented, and the logic behind it is laid out very nicely. So again, I'm not going to spend a whole lot of time on it, but the application of the Marcellus is that, like many of these shales, maybe more so than others, the bulk of the hydrocarbon storage system, the bulk of the porosity in the Marcellus occurs within organic matter. And you can see that in SEM. You can see it in relationships between porosity and TOC from all over the basin. These come from all the way up from, southwestern PA and northern West Virginia, all the way up into northeastern PA. So that's something that holds true throughout the entire basin where we've looked at it. The majority of the pore systems are in organic matter. And the problem that we had in the past was that we were basically double dipping, that you have this void space and there's this pore system that you're saying, okay, I'm calculating how much hydrocarbons in that pore space and getting my free gas in place. And then we're doing this adsorbed gas calculation based on absorption isotherms and TOC, and saying, and then, okay, I also have this adsorbed component. We're adding the two together. There's 50 BCF and one 50 BCF, and the other we have 100 BCF in place. But what we weren't accounting for was the fact that adsorbed gas takes up a portion of that free gas. It takes up a portion of that pore space when it's absorbed to these organic matter pores. So you're double counting this adsorbed layer because you're including it in the free gas and it's being included in the adsorbed gas. So you have to account for that. And so what the Ambrose-Hartman correction does then is it quantifies the volume taken up by the adsorbed gas and removes that from the free gas calculation. Now, what this does is not help us at all in this issue with the Marcellus, because it actually results in a net decrease in the gas in place. But at the end of the day, it is more accurate for what we're for trying to come up with the gas in place model. So we need to consider it there. And this is just some plots of total uptake experiments that Scott McCallum ran or had run. So what they do is they basically you take this core and you flood it with gas. So it doesn't care if it's free or if it's adsorbed or whatnot. You're just pumping gas into the sample at your reservoir conditions, pressure, temperature, saturations, all that, and just measuring how much gas it can hold. And what we found was that when our models didn't take into account the Ambrose-Hartman correction, they were over predicting the gas in place relative to the total uptake experiment. And then what we're looking at here is when we take into account the Ambrose-Hartman correction and compare that to the total uptake experiments, we have very good agreement between these. Now, again, that's under as received conditions. So that's, assuming a reservoir pressure and a water saturation, but it does tell us that the Ambrose-Hartman correction is a necessary variable to be considered. So then moving on then to the water saturation. So what's typically done is we retrieve this core, we get it to the lab, they cut a plug out, and it goes through an extraction process which takes those fluids out of the core. And then there's a measurement of total porosity, and it's always been assumed then that water was in the pore space, and therefore then you have a total porosity, you have this water-filled porosity, and the difference between the two is your hydrocarbon-filled porosity. And in our case, in the Marcellus and the gas window, that hydrocarbon is gas-filled porosity. But there's a number of issues that we have with this logic that's where that water is stored naturally. So one, and again, going back to this picture, we know that the majority of the pores that are in the Marcellus are in the organic material, and they're the result of hydrocarbon generation. So they're forming at or near peak burial as these rocks are buried into the oil and gas generation windows there. So these rocks are being subject to compaction and heat, which is largely driven off much of the water in the system. But more so too, these are hydrophobic systems here. So these don't like having water in them. So we have to come up with a way to put brines in pores that don't exist until we're well down into the hydrocarbon generation window, and we have to put that water into a material that does not like having water in it. The other problem we have is if we do, and we can do this with SEM images, we can quantify like how much of the pore system is in organic material and how much of it is in, intergranular material. There's not enough pore space in the intergranular material to account for that bulk volume water that we extracted from the core. So we may measure 4 porosity units of water, but we only have 2 porosity units of intergranular pore space there. So we're seeing more water than we think that the shale can actually hold. So the last thing to look at here too is if we look at the clay fraction of these rocks, anywhere we look in the Marcellus, again across the basin, the host rock clays are desiccated, which means if we measure the amount of water that's in the rock and we calculate how much water can be stored in the clay systems, we're always seeing a scenario where there's less water in the system than can be held by the clays. The other thing that's of interest here too is that, so this is a number of different wells, and you see the gray dots, the white dots, and the black dots represent 3 different wells. And they're just constantly kind of right there hanging out at just under 2% pore water volume, regardless of the clay content of these rocks, regardless of where we are. And so the water saturations that we're seeing seem to have very little, if anything, to do with the geology or the mineralogy. So again, we're in this situation where we have water, we have to come up with a reason as to why we would have water in a hydrophobic pore system when the hydrophilic clays virtually have no water absorbed in them whatsoever. So that's another issue that we've always had and struggled with to explain this concept of in situ water in the Marcellus. Now, in a totally different and unrelated project, one of the things we were looking at was when we were producing these waters back, could we tell how much water we were getting back from the frac job, and then were we seeing an influence from in situ brines? And in this work from Hitchin and Friedman in 1969 said, you have this meteoric water trend here, which is basically your frac fluid. You have this ancient brine end member, and you should be able to see a mixing trend through there. And we thought, well, we could do the same thing. And so Ashley Dowd started sampling this water from flowback. And the idea was we had the chemistry of the water we pumped in, and we should be able to see this progressing towards some ancient brine as production went on. And we saw this influence of the water. One of the first things that we saw that didn't make a whole lot of sense was that there wasn't, a normal trend of increasing towards that ancient brine composition as time went on. Rather, it was going back and forth through the system, back more towards the meteoric waterline, then to go back out towards more saline. And and this could have been different perforations or different frac stages opening up and flowing back and those sorts of things. But we thought we still can't say anything about that unless we know what the isotopic composition of that ancient brine is. And where better to get that than out of the core itself? That's full of this water. We should be able to extract that, get the isotopic composition of the ancient brine, we'll plot out there, and then we'll be able to figure out what's going on. And a similar study of this was done in the Permian Basin. Well, what we found when we did that was we extracted the water from cores. We had composition of the water that was used to build a coring fluid, and that's in the red triangle. And then when we start plotting the isotopic composition of the water coming out of the core, we realize that it's all over the place, and some of it shows absolutely no fractionation from the water that we used to build the coring fluid in the first place. And what we found after plotting this is that these values plot right along an evaporation trend that we would be expected to see from meteoric water. So what we argue based on this data set is that the water that we're extracting from the core is water that we have forced into the rock through the drilling and coring processes here. So that when we extract that water and we assume it's in the pore space, that's an error. That's an anthropogenic source of water, so to speak, that we force in there, and that the actual water saturations of the Marcellus are much, much lower. And if we run this as just a best case scenario, we can just assume that the water saturation is zero just to see what kind of answers we get. But regardless of what it is, we know it's less than what we're currently measuring, and that's going to result in a net increase in the gas in place values. So the third part of this I want to talk about and spend some time on is the fractures in the system, and what I've started to call a dynamic pore pressure gradient. So within the Appalachian Basin, there's as many as 5 different mode 1 catagenic joint sets that are within the Black Shale. And here's just some examples. This is in the Marcellus. There's some examples from the Dunkirk Shale here where you can see this. But all of these black shales in the Appalachian Basin carry these joint sets. There's 2 mechanisms by which you can generate mode 1 fractures. One is absolute tension. So you see this, it's a tensile stress, and that stress generally occurs in places like mid-ocean ridges and at the hinges of anticlines over a neutral fiber where the rock is warping this way, and you're in absolute tension above that, and you get these fractures. The other way to get mode 1 cracks is by generating an effective tension. And this occurs when you have a pore pressure in the rock that builds and overcomes the confining stress on the rock, causing the rock to fail then under effective tension as opposed to absolute tension. And there's a number of lines of evidence that I want to go through rather quickly that suggests that these fractures that we see all throughout the Marcellus and these other black shales in the basin are indeed the result of effective tension in our natural hydraulic fractures. So one, under absolute tension, high modulus rocks like sandstones, carbonates, those types of things, they carry the highest stress. So therefore, you would expect them to be the first to fail. So if these fractures that we are seeing were the result of some sort of warping event in the basin, say like glacial unloading or something like that, which these fractures are commonly ascribed to, we would expect then to see the carbonates and the sandstones and the siltstones to fail. But that's the exact opposite of what we see. So this is a very large northwest fracture running down this creek in the Rhine Street. And this is a zone of laterally persistent carbonate concretions. And this is a student realizing he doesn't want to be a field geologist, and that's why he's scowling there. But what you can see is this fracture goes in plane around these carbonate concretions. It doesn't have a stress high enough to cleave these carbonate concretions. This is the same thing that we're seeing in the Marcellus. So here's a carbonate concretion here. There's a northwest fracture. There's an east-northeast fracture. And both of these are going in plane around this carbonate concretion. Lastly, here's a siltstone layer in the Dunkirk Shale with black shales below it. And you can see that these fractures, they come up and they die at the base of that siltstone there. They're incapable of cracking it there. So again, if this was absolute tension, there should be no fractures here, and this siltstone should be fractured at a width that's about equivalent to the thickness of that siltstone bed. Another thing we find quite commonly is other indications that these are fluid-driven joints, ornamentations on fracture surfaces, arrest marks. This is because you build up a fluid pressure, you fracture the rock, you drop that fluid pressure, you build it up again, the rock cracks again, and that joint propagates a little bit further, and you get what they call these arrest marks. Other situations you can have is where you build up a fluid pressure, you fracture the rock, you bleed off that pressure, it closes back down. Now you can transmit a stress through that fracture again since it's closed, and then so you can drive another one right next to it. So that's why you have these really high tall joints that are very narrowly spaced here when you get these catagenic fractures or hydraulic fractures, because they're not subject to that mechanical layering like we would see, like we were just talking about in the siltstone. So, and I just gave it away there, but what do we think is causing this increased pore pressure? Well, in this case, we know it's catagenesis. It's the conversion of organic material to hydrocarbon. And you can see here's the black shale heavily fractured. Here's the gray shale underlying it. There's no fractures in there at all because there's no organic material to generate hydrocarbon. More evidence of that. So here is black shale out in the Columbus, Ohio area. We are at an RO about 0.62. So just getting into the oil window, a little bit below the onset of oil generation, and we don't see any fracturing in that black shale at all. We move a little bit further. This is outside of Buffalo, New York, and now we're at a 0.77 RO, so we're starting to get up into through the oil window, and we're seeing fractures being generated here. And then we move even further east into the Syracuse meridian. We're at a vitrinite reflectance of 1.3, and we see it's just heavily fractured black shale here in this instance. There, so that's saying the increasing thermal maturities, increasing the hydrocarbon generation, leading to more fracturing in the rock. Now, another interesting thing, this was an observation I made in the Cleveland area. This rock here is Cleveland Shale at about a 6 weight % TOC, and note how heavily fractured that rock is. But then when we move up into these beds to about 2 weight % TOC, there's little to no fracturing other than what's carrying over up from these beds down below. Likewise, when we look at fracture spacing in the Rhine Street, we see there's virtually no relationship between organic carbon content and fracture spacing until we hit about 3 weight % TOC. And then we see that the fractures get more narrowly spaced and more abundant as TOC increases. Again, what this stuff is here is likely you're seeing fractures that are forming in more organic rich beds and those are coming up through higher, less organic rich units. So what that's telling us is that the TOC is controlling overpressure within these rocks there, that you don't have a constant pressure within an entire Marcellus unit or Rhine Street or Barnett or whatever you're looking at, but that overpressure is varying as a function of the generative potential of these rocks through there. So what what else is interesting about this is that when we look at program pyrolysis data, we find that a lot of these rocks, they're pretty much spent, they're pretty well fried, but they still do have some residual hydrogen in there, suggesting that there may be some minimal generative potential to them, which suggests then that uplift of the basin occurred prior to completely exhausting the hydrocarbon generative potential of these rocks. So what that tells me is that these rocks, they're generating an overpressure, they're fracturing and bleeding some of that off, and then they're closing down when they come back down to the minimum horizontal stress gradient, and then it gets uplifted there. So these rocks then are probably, it's possible that they are in close equilibrium with the minimum horizontal stress gradient. And so what we can do then is just build a simple model, which is what I did here, was go from saying we're going to assume we're normally pressured if there's no TOC in the rock, and up to about 3% TOC, we're going to see that reservoir pressure is going to start climbing as we get more organic rich beds with a higher generative potential, until we get to around, I chose about a 0.9 because we find that rocks that weren't fractured at all, like in the Utica Point Pleasant, they have no evidence of catagenic fracturing in them, and they're right nearly at the minimum horizontal stress gradient there, which is right around a 0.9 to a 0.95, and then I sort of just leveled it off here. So this is theoretical, and I fully acknowledge that, but it's based on some actual data and field observations as well, so that we can build this model. And what this does is it results in a net increase in gas in place when you start to account for the fact that some of these beds are at a much higher reservoir pressure gradient than if we just use an average that we get from like a DFIT test. Now, the one thing that I will say about that is it's important to note that, again, these fractures, they generate hydrocarbon, the rock cracks, that bleeds off that pressure, and then they close back down. So because of that, at depth, they're likely closed, which also means they're going to be very difficult to see on image logs. That's why you generally only, you mostly see the calcite filled fractures on image logs, and they're vertical. So unless you have imaging in a horizontal well, which we've done, they're difficult to see, but you can see them. But so they're likely going to be closed at depth. So they're not they don't have gas in them. So they're not necessarily a source of gas in place, but they're a source of communication, and they're evidence of varying pressure gradients. But when we pump in that small volume of water to do the DFIT, we open up all of these fractures. So in essence, you're increasing the reservoir volume. So when we do that calculation to come up with a reservoir pressure gradient from a DFIT test, I think we're underestimating it, because we're opening up a bunch of fractures that don't have any volume or minimal volume associated with them in a natural state. And now we're opening them up into DFIT, and that therefore increases the volume and therefore decreases the calculated reservoir pressure and subsequent pressure gradient. So if we take these considerations, and this is just a random example of just a random well that I pulled, but when we use the old methodology, which is this here, which is using a variable water saturation, so we're assuming the water saturation is real. We are using the conventional method of free and adsorbed gas in place. We're not using the Ambrose correction, and we're using just a static reservoir pressure gradient, like a 0.72 or whatever. We get about 78 BCF per square mile. But if we change that to where we assume that the water saturation is 0, we use the Ambrose correction, and we assume a dynamic pore pressure gradient, we end up with 93 BCF in place, or an increase of about 20% to our gas in place values. So if we compare those slides I showed way back in the beginning of this here, so this was what we had under those normal, or the old way of doing things. If we add 20% to that gas in place, we can see we start to drop these numbers down to levels that are maybe more reasonable, or people maybe feel more comfortable with in terms of the recovery. Now, I wanted to switch gears a little bit, because I can't say without certainty that there aren't other beds outside of these black shales that we're actually targeting that are contributing to the gas in place. And I needed a transition slide there, so I just put in, this is actually this eternal flame in Dunkirk. This is actually methane that's seeping out of a fracture that is lit pretty much all the time. And it looks pretty neat, but I also realized when I put this picture up that the fall leaves and the flame look identical. But that's the flame right there burning there, so that you can all see that there. But you know, this is gas that's not necessarily coming from this rock right here, but it's connected to rocks elsewhere and continually sourcing this flame. I mean, that's been lit for decades. So one interesting observation that I wanted to show is in these this unit right through here. So this is in the gray shale section of the Hamilton group here. And what we know are these low density units that are coming in here. We see a number of them here. We see a couple through here, and then they're largely gone, although we can see there's still a little bit lower density through here. So this is the Marcellus down here. This is the Lavana, which is the black shale that sits on top of it there. People often call it like the Marcellus 3 or something like that. It's actually not part of the Marcellus, but it's black shale and it contributes to the gas in place. So we count it in there. Then we get this unit of gray shale through here, and then you're up into this unit that I'm interested in right here. And if we look at the character of these, there are these, we see these gamma ray increases up through here, sort of these, I would argue more like a transgressive signature through here. They often at the base of them show a spike in PE and then a upward decrease in density. Now, in this particular example, we come up with like an average TOC of these shales around 4%, with measured TOCs in excess of 8% in some of these. It corresponds to a significant accumulation of hydrocarbon, an additional 30 BCF right there. You know, that's more than the 20% that we gained out of modifying the model. So what I think these are, what we're seeing are evidence of, are black shales that are probably overlying some sort of little diastem unconformity. And what I want to look at is the Ledyard shale. So this is a neat area. This is an outcrop in up in New York State in the Finger Lakes area. It's at Moonshine Falls, like right on this picture. If you go downstream a little bit more, it's like a 100-foot waterfall there. But this is Centerfield limestone. And at the contact, you have this phosphatic pyritic lag deposit right here. So the pyrite, the phosphates, all that's going to give you that really high PE kick that we see at the base of these black shales in the log. Then overlying that is this organic rich, well-jointed black shale that's in the Ledyard here. And what probably happened was you had erosion, invasion of a low oxygen, anoxic to eosinic sea. Carbonates and those things are not stable under that, so they're dissolved away, and you end up being left with this lag of insoluble material like pyrite and phosphates and things like that then are eventually overlain by black shale. Now, if this occurs over a limestone, you tend to see more like sandy phosphatic material. If it occurs over a gray shale, you'll see more phosphatic and pyritic material in there in that lag. And this is the model of that here. So what you can see here is that we have erosion of this channel down into the underlying units here. This is where you would have that phosphatic or pyritic lag, and then black shale deposition within that channel. These things are, 10 feet high or tens of feet high, and they're, tens of miles across here, which if you go back to look at that cross section here, again, these are about, in the tens of feet thick. And when we look at these black shales and trace them through this cross section, they're in that tens of miles wide range before they seem to pinch out there. So I think that what these might be are discontinuous channels that are filled with black shale, which may also explain why some wells have a much higher than expected recovery factor, while other wells on nearby pads don't. Another thing that needs to be considered, I think, is communication with the Geneseo Shale overlying. When I was working at EQT, we had this problem in areas where we had a thin enough Hamilton. It seemed that we would have communication with Geneseo wells that we had drilled there. And it seemed that they were at least sharing reserves, if not producing the Geneseo gas out of the Marcellus wellbore. So I conducted an experiment. My thought was, well, okay, if we're producing Geneseo gas out of the Marcellus, we should see, if we drill the well through the Geneseo, we should see evidence of depletion in that rock if it offsets a Marcellus well that's been producing for a significant length of time, which is, around like a year or so, I think is what we decided to conduct these experiments are. So we ran geochemical mass spec in these wells, and I looked for depletion in the form of an increase in gas wetness or a decrease in helium. So helium accumulates in porosity. So if you produce what's in that pore space, you reduce the amount of helium, and you preferentially produce the lower chain hydrocarbons relative to the higher chain hydrocarbons. So your methane, your C1 will go first. So your wetness should increase in a depleted zone because you preferentially strip the methane out and left all the higher chain hydrocarbons. And what we found was, and this is, I just drew this, but it's something like this where you would have a relatively constant profile. Then you would see like this discrete zone of an increase in depletion, which would then go away. And these zones, they didn't necessarily correspond to where the well bores were closest to each other, where you might expect, where like fractures, that we emplaced were interacting with each other or anything like that. Sometimes these wells were furthest apart, and we'd see this happen. And what I offer might be occurring here is encountering gas chimneys. So this is an example of a gas chimney that overlies the Geneseo Shale at Tyhannock Falls State Park. And so what these are very discrete zones of incredibly heavily fractured rock, and they often extend up off the tops of these black shales. And what I would argue is that if you have gas chimneys that are coming off of the Marcellus, and you have a thin enough Hamilton or in clay-rich enough Tully, which we fit all those criteria in different areas, you could have gas chimneys that are coming off the Marcellus and interacting with the Geneseo, such that you might be drilling a Geneseo well and everything's normal, and then you drill through an area that's in communication with a gas chimney, and that's where you see this depletion because you were able to, your fractures in the Marcellus came up through these gas chimneys and up into the overlying Geneseo, and you started producing that gas through there. Then you come out of the gas chimney and you're back into rock that doesn't show evidence of completion because our induced fractures in the Marcellus didn't make it up through there outside of the gas chimneys. Now, the last thing I wanted to talk about then is more ubiquitous fracturing. Now, in the last one, we talked about the fact that, these are discrete intervals, and it is generally what we see, but it is worth noting that not only do we see with increasing thermal maturity, do we see increasing fracturing within the black shales themselves, but as we really start to generate hydrocarbon, we see those fractures producing enough pressure that they actually crack up and out of the black shales and into overlying units. So here's an example of black shale, gray shale contact in the Lake Erie region of Western New York, where you have lower thermal maturity, and these fractures are largely confined to the black shale, don't extend up into the overlying gray shale. Here's an example in the Finger Lakes region where fractures that were generated in the Geneseo actually come up out of that unit, and you can find them in the higher units of the Ithaca there. So there is also evidence that we could have communication through fractures that continue from these black shale units up into overlying units if we have the proper lithology and amount of hydrocarbon generation to source those. So with that, I think that's the end of the talk there. I just wanted to say thank you for your time. Here's my website if you want to explore around there to see some more of what I'm up to and what I do. There's a blog on there and whatnot of different aspects I'm thinking about and stuff that I'm working on. And there's my email if you want to get in contact with me to talk about anything else. So thank you.
Appreciate that, Randy. Thank you for the talk. It was tons of pictures, very pretty. Makes me jealous. So I need to get out more, I think. I
put this picture here at the end, which has absolutely nothing to do with black shales in the Appalachian Basin. That's actually a job I had collecting samples for a client out in the Powder River Basin. But basically, just to drive that point home, you need to get out and look at rocks wherever you can. And so that's my mobile office there when I'm out in the field. Mobile office and house.
Yeah, it's been a little bit since I've been out in the field, so I'm overdue. I'm overdue, definitely. Well, I wanted to go ahead and get the Q&A started. We do have some questions that have been submitted. I figured we can, you and I can go through them really quickly. And the first question is, you mentioned the rocks are not water wet. So if the sediment started with some connate water, was the water diffused as the gas was generated and displaced the water? Question mark, or what?
Yeah, so that's a good question. And so there's a number of different ways to drive the water out of these systems. One is just through mechanical compaction of these shales. These things start off at somewhere around 80% porosity, and they seem to hit, like in the Rhine Street anyways, we hit a fluid retention at around 30% porosity or something like that. So there's a mechanical compaction that will wipe out 50% of that porosity and the fluids that are in there right off the bat. And then I think through heating of these rocks too, we're also, have a tendency to vaporize and move water out of the system that way as well. And indeed, you can also have the gas generation can also be driving fluids out of these rocks in front of it as well. Now, I do know that, especially when you look at a lot of these cores in the subsurface, a lot of them have calcite-filled veins in them, some of which are vertical, many of which are horizontal, and that's later stage fluid migration. That's fluid migration that's occurring, at the same time some of these other fractures that are forming in the basin. And you also see a prevalence of them as you approach the structural front. I think Mark Evans did an excellent study of that. Like where we work out in the Finger Lake or out in the Lake Erie area, you don't see any calcite-filled veins at all, but you see them, all throughout our cores in the subsurface as you approach the structural front. So that's a subsequent fluid migration, into these rocks, at least into these fractures afterwards.
Awesome. Appreciate that. We got another question as well. What is the salinity of the in situ pore water? Also, are the plugs kept in a desiccator until just before plug measurements are performed?
So I think the salinity of these pore fluids, they get up to in the flow back anyways, like they can exceed 200,000 parts per million. So they get pretty saline, but it seems to happen fast. We seem to go from very, very fresh water to suddenly very, very saline water. And what we think is happening is you have a lot of these ions are electrostatically held to clays. And when you introduce that water to these desiccated systems, they take all those ions, and then that's where that high salinity is coming from. So it's basically stripping ions off the clays that are in the shales already there. As far as the exact measurements, I have kept in a desiccator until the plug. I'm not sure about that, Neil. I'd have to go back and check with the labs.
Awesome. Well, Neil also had another question there. Are there any B fractures in the Marcellus as well as vertical fractures?
So okay, that I think depends on whether or not you use the narrow or the broad definition of B fractures. And my understanding is that the beef is what you're actually seeing is crystal growth. As this fracture opens up, the crystal growth is keeping pace with that. And so you almost have like a central seam, and you're seeing, crystal growth coming off that seam to either side of the fracture face there. It seems that more generally, they often refer to beef as just any horizontal calcite-filled fractures. So that we most definitely see something. If you want to fit it to the general definition of beef, we do see horizontal, sub-horizontal calcite-filled fractures, and that are by themselves of varying thicknesses, of swarms, those types of things. I don't know that I would say that I've seen anything that fits the narrow definition of beef.
Okay, appreciate that. On to our next. It says, is there any way to see gas chimneys without seismic as the Geneseo continues to be in delineation?
So yeah, another great question. I don't know, largely because I don't know of anybody looking for them in these onshore Paleozoic rocks. I know that offshore, especially with the gas hydrate world, they talk about them all the time. Matter of fact, I just got done reviewing a couple dozen gas hydrate abstracts for AEPG, and I'll bet 80% of them mention gas chimneys in the discussions of these, which may have something to do with how these things are forming. So I do know that the answer to the question is yes. You can see them with seismic. I don't know that you could see them in seismic in this basin, and I don't know that there's a way to see them without seismic in this basin, largely because we haven't. I don't know. We've seen anything definitively in the subsurface, say with like an imaging log or something like that says, oh, that looks like a gas chimney right there, and then try and corroborate that with a seismic signature or something like that. I would think that I don't know to what degree that they have a predictability to them, where you could say in these areas, due to these conditions, like you'd expect them every like 3 or 4 miles or something like that. So I don't know that there's any way of identifying them without actually drilling a well and realizing then that you've subsequently encountered one. Now, I will say that although that's not predictive, it can help in terms of spacing out your completions. If you are running something like geochemical mass spec, which I don't think is a very expensive tool to be, putting on these wells, you could definitely identify zones where you're like, okay, this is depleted. Maybe it's because of a gas chimney, and we're going to avoid, fracking stages within that zone there. So I do think that there's stuff you could do to identify them while drilling. I don't know if you could identify them before drilling without seismic.
Awesome. Then this other one, fantastic talk. Thank you for this. What percentage of the gas in place is contained in the natural fractures? What moisture content did you use for your isotherm measurements?
So I don't think that in the subsurface, I don't think these fractures are open. There's probably, just from cracking the rock open and closing them down, there's a minimal amount of porosity in there. But like, you know, when you look at these pictures here, and these pictures, these are open like that because they're at the surface. So is this stuff rebounds, you're dropping the confining stress on the rocks, and therefore the rocks have the room to expand. But instead of just breaking, again, they just open up on these existing fracture networks. So these things have a definite volume to them at the surface. But in the subsurface, I don't think they do. I think that they've bled most of that gas off, and then they close back down. And one of the reasons for that is that even in horizontal imaging logs, they're very difficult to see. And oftentimes the only evidence you have for them is when you are encountering the east-northeast fracture set, which is parallel to the contemporary stress field. So it's in the parts of the wellbore that are in tension, and they open up on the image logs there. So you can see them, and we've seen them down in, like, you know, northern West Virginia and the subsurface and whatnot. So I don't think the fractures hold a whole lot of porosity to them, or gas in that storage mechanism there. The isotherms, they were run at the saturations that we received from the core. That was all done before we had considered, you know, any ideas behind, you know, that water saturation not being in situ.
And just, you know, as a follow-up that I have on that question and your response is, so maybe if you were fracking the well and you are now depleting the well, you know, through production, would you think in the subsurface that some of these fracture networks may start to assist with the EUR down as the well's life continues?
Yeah. So I personally, I've never had a big issue with high recovery factors in the Marcellus. I think a lot of that was coming from people who were used to seeing things in like the 30% range. And then you start seeing like 75 and 80, and they're like, that can't be right. But there really isn't a reason that it's incorrect. You know, I mean, as long as it's below 100, you know, and you know, in these models, they have, you know, 10% error in them anyways. So I would say even as long as you're below 110%, I wouldn't be too awfully concerned with those recovery factors. And I think part of that is because of these pre-existing fracture networks that are ubiquitous. It really increasing the surface area of these rocks and the ability to produce, you know, that hydrocarbon out of them. I have a little bit of experience, you know, working in other, you know, I've worked in Mowry, I've worked in Barnett and things like that. And you don't see these fracture networks, you know, to this degree, I don't think, you know, in some of these other plays like you see in the Marcellus. But when you start depressurizing these rocks, so there's a couple of things that happen. Is one, the effective stress on the rock it's reduced because of the pressure associated with the hydrocarbon in there. So if you remember your effective normal stress equation, it's the normal stress minus the pore fluid pressure, and, you know, some other terms in there, but that's the bulk of it. So you have the total normal stress on the rock minus the pore pressure, but you're constantly reducing that variable by producing the rocks. You're actually increasing the effective stress on the rocks, and which I think could have a tendency then to start, you know, closing down pore networks, fractures, things like that, because you're taking away what's keeping all this stuff open in the first place down there. So I think that might manifest later in life as a more steep decline than maybe we're expecting to see in the well production, as, you know, we hit some threshold where these rocks, you know, they can't stay open. And I know I'm going off course here, but what else is interesting is that these pores, they start to form in the black shales before mechanical compaction has stopped. So we find that if you have a lot of biogenic silica, the permeability is higher than if you don't have as much biogenic silica. And what I think is happening is that in some instances, that gas-filled pores in the organic material is probably supporting some of that overburden pressure and some of that confining stress. And as you produce the rock, you're taking away that support, and those organic pores are starting to collapse and shut down permeability as well. So,
okay, awesome. I appreciate that. Seems this underestimation of Marcellus gas in place is largely related to the desiccated nature and Marcellus combined with currently healed fracture networks produced at depth from hydrocarbon generation. Is there an example of another shale reservoir with these characteristics where this phenomenon is observed?
And again, you guys are Houston based, everything operates out of Houston. So you probably, work a lot more of these plays than I do. But this gets back to the, unique versus non-unique solutions to this issue in the Marcellus. So I'm going to say, to the best of my knowledge, this is the only place where we see this happening. I don't know about the I think the desiccation thing is something that could be happening everywhere. All of our coring, methodologies and, from at least the differences from lab to lab, but our measurement technologies are all roughly the same. So I think anywhere you have the opportunity to be forcing water, not only into the core, but into the surrounding rock too, which is why you pick it up in the logs there. So I think that's happening, but, the differences in the amount of fracturing, the type of fracturing you get, the number of joints and the joint orientations, that's a result of, what stresses are being applied to the rock when it's reaching the hydrocarbon generation windows, what the organic carbon content of these rocks are, what the overlying lithology is. Like, for example, the Point Pleasant and, probably like parts of things like the Eagleford and things like that. I mean, these are more carbonate rich rocks, so they're a harder rock and they have a lower organic carbon content. So you have to have less organic material generating a lot more pressure to break a much, much tougher rock. And, and that's going to be very, very difficult. So I don't know that the situations that lead to this, ubiquitous fracturing throughout the black shales in the Appalachian Basin is something that you see all the time everywhere else. I mean, I know I've been like out in the Mowry, for example, just last summer, I didn't see any evidence of catagenic fracturing in that rock.
Appreciate that, Randy. Appreciate that. Well, we've got two more questions left. I figured we can keep it at that. So if there's anybody who's thinking about asking another question, please feel free to reach out to Randy directly. I think you saw his email there. You can also reach out to the HGS office and we can put you in touch. So I'll get these last two questions knocked out and then we can shut her down because I know everybody's probably in the middle of their day, got stuff they got to get back to. So the next one is, it's fascinating seeing these findings at the outcrop lab scale as similar trends are seen at seismic scales from structural reservoir volumes across the basin. That said, do you feel in the in situ conditions of the black shales takes precedence over structural overprint that is present in the basin?
I let me know, Dylan, if I'm answering this question the way you want me to. But I would argue that the in situ conditions are what's going to, that's what's going to affect the production of the wellbore. The current stresses that the rock is subjected to right now are going to play the most prominent role. Now, again, that being said, much of those, we see evidence of relic stress and residual stress in these rocks all the time. So I think that the in situ conditions that we see right now, they still harken back to some of those stresses that were present in the basin at the time these rocks were being buried and fractures were generating and whatnot. So but in the end, the current stresses and conditions that those rocks are under right now is largely what's going to control that production. It's just going to be influenced by all those diagenetic and structural processes that have occurred to that rock through time.
Okay, thank you. Awesome. And then on to our last question is, as operators play around with water and sand concentrations, it would seem that these fractures would expand to accommodate the water and sand volumetrically. However, with time, my mental model would suggest that the sand component is critical to long-term productivity, while water would be important in initial productivity. Perhaps this is being answered currently.
No, I think you're absolutely right. And that goes back to the effective normal stress on the rock, in the sense that as you produce the hydrocarbon, you're going to increase the stress on the rock, and therefore the chances for closing down of fractures, proppant embedment in more clay-rich horizons, all that is going to be the Poisson effect. It's all going to be exacerbated and become more of a problem as time goes on. This is why I was always such a huge proponent of targeting in the Marcellus. I think we're all geologists here, so I can say, that like the engineers, like they want like a 200-foot window so they can just do whatever they want at 1,000 miles an hour. And when you come back and be like, no, it's a 10-foot window, they get really, really bothered by that. And but the reason for that is because we're targeting rocks that have the highest porosity, the highest occurrence of biogenic silica, and therefore the highest deliverability, so that we're in the rock that's most likely going to be able to stay open and produce through time. Because if you drill such that you're either in clay-rich material or you have really good reservoir between your wellbore and the clay-rich material, that's going to form a pinch point as you start to produce these rocks and increase that effective stress on there, and you're going to end up stranding a bunch of gas behind those pinch points there. So yeah, and I think like you're saying, with the water and the sand initially, that's going to inflate this whole system. But as you produce that water out, you're going to be, and you'll be able to produce that entire section there and assign an EUR based off of that. But as time goes on, yeah, that water is going to be drained out of there. You're going to be left with just the sand holding that stuff open, and it's going to have to hold it open either in really good rock that's much easier to hold open, or it's going to have to try and hold open rocks that aren't ideal and to hold open. And I would think you would want to be producing through those less than ideal rocks early on, and not have to be relying on them later in the life of the well when all you have is sand trying to keep fractures propped open.
Awesome. Well, we had a quite an active Q&A session, Randy. So obviously your pretty pictures, your just all around demeanor elicits lots of thought-provoking questions, because that was a good session. So well, thank you for so that. Much. I just want to thank you on behalf of the Houston Geological Society for taking time out of your day to share with us, share with the membership your thoughts, your findings, and it was really exciting. So appreciate that, really do.
No problem. Thank you so much for the invitation.
All right. Well, with that, this will conclude the general lunch, HGS general lunch event for today. Like I said, if you have any questions or you want to reach out to Randy, you can see his email here on the screen, randy@drbgeological.com, or you can reach out to the HGS office. We can put you in touch. Either way, that works out. So with that, I'll let everybody get back to their day. Stay tuned for future events and look forward to seeing you guys again. Thank you so much.
Thanks, everybody.